Yo, alright, so I low key clickbaited you in the title, but not that much, cause I'm gonna explain the counterintuitive result later on in the video. But in this video, like the main goal is for me to teach you limits and continuity in higher dimensions, and at the end, I'm gonna show you a counterintuitive result revolving that. Just be patient. Alright, so we know the general idea of a limit, at least the informal idea of it. Says that if x approaches this value c from from these two sides, f of x approaches the limit as x approaches c. For example, here, let's say f of x, and we take the limit of f of x as x approaches 0. We could just plug in 0 here and get the limit is 0. And we say that the limit only exists when the limit approaching from the right side, or the positive side, is equal to the limit as x approaches c from the left side, or the negative side. So x needs to approach c from both sides, and in turn that will make the limit, if it exists, the same for each. For example, here, when x approaches c from the left side, it's obviously a different value than the limit as x approaches c of from the right side. So we say that the limit as x approaches c does not exist. Great, but we need to find a way to do this in higher dimensions, or in this case, just the third dimension. We could also do fourth dimension, nth dimension, but like we're just gonna do So we know that the domain of any single variable function is just a number line, or an interval on the number line. The domain of a two variable function, f of x, y, would be a subset, or just the entire plane. So the domain of our function f can be any subset of the plane. Now, if we want to take the limit as x approaches this point, xo, yo, we want the limit to exist. So now, instead of approaching from left to right, we need to approach from all sides. We need to approach from this side, from this side, from this side, from wherever, from every side. So we need a proper, rigorous way to define a limit to account for all the sides. And of course, we actually have that. And it looks like this. Now this looks really complicated, but I'm about to explain it. This is saying the limit as xy approaches any point of f of xy is L if, or the limit exists if, for all numbers epsilon greater than 0, there exists a delta such that for all points in the domain, the absolute value of f of xy minus the limit is less than epsilon when this root right here is less than delta. Basically, what this is saying is that the distance between f of xy and L becomes arbitrarily small when the distance between xy and xo, become arbitrarily small. By the way, the points xy we're talking about should be, we're saying them as they're in the domain of f. In this definition of a limit, delta is the radius of a disk centered at xo, or centered at the point we're approaching. And this is just saying that whenever we're approaching xo, the point that's approaching xo is always going to be in a disk centered at xo with radius delta. And that point always maps to a point on this interval in the z-axis. And we can see that the absolute value of f of xy minus L is always going to be less than epsilon, since here this length is just epsilon. And this limit definition is good for actually all limits, because it considers every direction for this, because it considers every direction because of this. This is just describing a disk. And we can also do a lot of stuff with this definition. Here I've just circled the main part of the definition. And we can actually use this definition to prove that the limit as xy approaches xo of just x is just xo. First part of the proof is writing this as less than delta. Also, we're not doing the second bracket for y and yo because we're not considering y here. We're just doing x. Next point is the next step is realizing that the root of a square is just the absolute value of the thing you're squaring. So this is just the absolute value of x minus xo. And since here x is just f of xy and xo is just L, which is the value of the limit, so that's just the same thing as saying f of xy minus L, which from here it's less than epsilon. So given any epsilon, we'll just, if we make a delta equal to epsilon, up here we showed that the root of x minus xo squared is less than epsilon, and if epsilon is equal to delta, we get this, satisfying the definition for a limit. So we've just proven that this limit is just xo. Now we move on to the properties of the limits of multivariable functions. So these are the 5 main properties of limits of 2 variables, which is just the same as one variable. We have that the limit of the sum of 2 functions is just the sum of their limits, and the limit of a constant multiple of a function is just that constant multiple times its limit, and that the limit of the product of 2 functions is just the product of their limits. The limit of a function raised to a certain power is just its limit raised to that power, assuming it's positive integer, the power. And the limit of the nth root of a function is just the nth root of its limit. Of course, assuming that n is a positive integer, and if n is even, then we assume that L is greater than 0. Since you can't take the even root of a negative number, it can't possible. Now the formal proofs for these properties are too long for this video, and they're not necessary for the purposes of this video. So informally though, you can just notice that when xy is really close to xoyo, then f of xy is close to L, and same for g of xy being close to m. Then from that you can informally deduce these properties. So for example, this limit here, we can just substitute 0, 1 for xy to get us 3 on minus 1, so just negative 3. And for this one, we actually can't just do direct substitution because the denominator would be 0, so we need to do some algebra. Alright, so here I've just factored it out, and plugging 0, 0 in for this, we just get 0. Alright, now we have this limit, and what you'll notice is that we can't factor anything into anything that would be useful, like that would cancel out factors and numerators and denominators. Nothing we can do. But what we can do this analytically. We can sort of approach the origin from two different directions and see what we get. We're going to notice that approaching the origin along the line y equals 0, the limit is just always going to be 0 because we're multiplying 0 by something. And same thing with the line x equals 0, the limit would also be 0. Now that's just accounting for 2 directions. We need to account for all directions, and we do that with the limit definition. Just to remind you, we need to show that there exists a delta that satisfies this condition when we're given any epsilon that satisfies this condition. First, we'll just simplify these absolute value brackets to get this, since y squared, 4, and x squared plus y squared are all positive. We next need to observe that since y squared is always less than or equal to x squared plus y squared, if we divide both sides by x squared plus y squared, we get that y squared on x squared plus y squared is less than or equal to 1. If you multiply both sides by 4 times the absolute value of x, we get that this. And we can actually just rewrite absolute value of x as the root of x squared, which is always less than 4 root x squared plus y squared. So if we make delta equal to epsilon, a fourth of epsilon, we've just shown here that this is less than 4 times square root of x squared plus y squared, which is less than 4 delta, since over here, if we just multiply both sides by 4, we get 4 root x squared plus y squared is less than 4 delta. So we get that this is less than epsilon when delta is a fourth of epsilon. So the conditions in our limit definition, we've shown that those are satisfied with this when the limit is 0. So we've just shown that the limit of this is just 0. Alright, last example. If the function we're taking the limit of is y on x, is the limit of this as it approaches 0, does it exist? So to answer this, we're not gonna approach along the line x equals 0 or the y-axis, because x can never be 0 here. In other words, the y-axis is not in the domain of this function, so we're not going to consider those. We're going to notice that along the line y equals 0, as we approach the origin along this line, the function approaches 0 because y is 0, so 0 on anything is just 0. Now we're going to approach along another line, y equals x. If y equals x in this function, it approaches 1, because if y is x, then this is always just 1, so the limit is 1. So we have two different lines of approach here and two different limits, so the limit doesn't exist. Now we're going to define continuity for functions of two variables. And it's just the same thing how we defined it in... Someone messaged me. Someone emailed me. Anyway, it's just the same how we defined it in single variable. We say that a function f is continuous at a point x o y o if 1, the limit as xy approaches x o y o of f exists, 2, if f is defined at x o y o, and 3, the big main one, the main big one, is that this limit is equal to f of x o y o. So we'd say that, I don't know, if f of x y was x, we would say that this function is continuous at, for example, the origin, because the limit as the point approaches the origin of x is just 0, and f of the origin, or f of 0, 0, is also 0, so the limit is equal to the function value at the origin. So we say that this is continuous. For another example, let's say we have this function, this piecewise function, is defined as this for xy not equal to the origin, and then at the origin the function is just 0. So we're going to ask, is this function continuous at every point? After all, it's actually defined at the origin since it's piecewise like this. And maybe the limit would just be 0 of this, so let's take that. So here we're going to do this limit along the line y equals mx. So we're going to be approaching from every line every straight line toward the origin, since when x is 0 here, y is also 0, so it would be at the origin. It would have a point at the origin. Anyway, we're just gonna substitute mx for y here to get this. Now we can factor out an x squared out of every term here to get 2m on 1 plus m squared. Notice that for any m that's different from another m, or any slope of the line that's different from another slope, this value changes. The limit changes as if we change the slope of as we're approaching the origin. So since two different straight paths, since two different paths give a different limit, this limit does not exist. So the limit doesn't even exist, so this function is not continuous at the origin. But it is continuous at every point beside the origin, because to take the limit as the point approaches any point besides the origin of this, we can just plug in the x and y values to get a function value, and then we can just do the same thing to get the limit. Alright, now let's say we have this different function over here. We're going to ask ourselves, does this have a limit as we approach the origin? And to do that, we're going to do the same thing again. So we're just going to do the same thing again, approach along any straight line going towards the origin. So this limit over here is just this limit as x approaches 0. We can factor out x squared out of every term to get this. So this limit would approach 0 as x approaches 0 for any m. So the limit as this approaches the origin would be 0. Wrong! Let's now take the limit as xy approaches the origin along the line y equals mx squared. This limit would just simplify to this, and we factor out an x to the 4th out of every term here to get this. Different values of m would give different values for the limit. Therefore, the limit does not exist at the origin. And now we come to the conclusion that I was promising to show you at the start of the video, the counterintuitive one. We've just shown that having the same limit when approaching a certain point along every possible straight line does not imply that the limit exists. When you first conclude this is like really counterintuitive. Because when I first heard of this, I was like, yo, like that's crazy, bro. Like that's kind of weird, bro. Cause think about it. If you approach a point along from literally every single straight path towards it and get the same limit, you would expect that, you know, the limit actually exists, and that is the limit. But no! You need to consider all possible paths, all possible curves. So this one, freaking, this one, that one, this one. And we can actually show that a limit exists using every possible approach path, like literally every single one. Let's say we have this function of xy, and it's y plus sine x on x plus sine y. Now if you take the limit of f of xy of this along y equals f of x being, can literally be any curve, and we're using this to approach the origin. There's some things to note. First is that f of 0 is 0. Since when x is 0, y also has to be 0, since we're approaching the origin here. And yeah, that's it. That's the only one. I don't know why I tried to mention another one. we can simplify this to, or not simplify, we'll just plug in y for f of x here to get this. If we use direct substitution, since f of 0 is 0, we get 0 over 0. So that means we can use L'Hôpital's rule. We can use hospital rule, bro, my favorite rule. Using hospital rule, we get the limit becomes this. Now if we use direct substitution, we get f prime of, I'll just write this. If we use direct substitution, we get f prime of 0, and cosine of 0 is 1, so that's the numerator. And on denominator, we get cosine f of x is just cosine 0, since f of 0 is 0. So 1. So 1 plus f of f prime of x is what that simplifies to. And this whole thing is just 1. So the limit as xy approaches 0, 0 of this function is 1. And that's along literally every path approaching the origin of this. All in all, I just wanted to show you this pretty cool result that if you approach some point, it could be this point. If you approach any point along every straight line of a function in its domain, and you get a certain limit out of that that's constant for all the straight lines, that does not mean that that is the limit or the limit exists, which I think is a pretty cool counterintuitive result. I just wanted to show you that. Alright, bye.